Have you ever looked at the sheer scale of these really powerful AI models, especially the huge language models, and just wondered how on earth do we keep making them better without them becoming, you know, impossibly huge?
Or ridiculously expensive, right?
Yeah,
Or just too power hungry for the planet.
exactly. It's a massive hurdle for anyone working with this stuff or even just thinking about advanced AI.
It really is the core dilemma. Scaling up these transformer-based
Mm.
LLMs, large language models, it just demands incredible amounts of computation and memory.
Which makes them super costly,
Yeah,
both to train and then to actually run to deploy.
absolutely. And, historically, the efforts to make them more efficient have usually gone down one of two paths.
Okay.
Either parameter efficiency, that's trying to shrink the number of unique weights in the model, or adaptive computation.
Which is like only using compute power when you really need it.
Precisely.
Yeah.
Spend compute only where it's truly needed. But it's been rare to see both of those approaches tackled together
Yeah.
at the same time in one system.
Right. And that's exactly what we're diving into today. We're exploring this really fascinating new framework. It's called Mixture-of-Recursions, or MoR for short.
Oh, yeah.
And this isn't just some small tweak, right? It sounds like a totally unified approach. It cleverly combines both parameter sharing and that adaptive computation thing.
All within a single recursive transformer. It's quite elegant, actually.
Okay, so our mission today then is to unpack exactly how MoR pulls this off.
Yeah, we'll get into the mechanics, what makes it so different, and why researchers are calling it a new Pareto frontier in LLM efficiency.
A new frontier? That sounds promising.
For anyone building or deploying these models, it suggests you can get large model quality without that crippling large model cost,
Hmm.
which makes powerful AI potentially much more accessible and sustainable.
Okay, I'm ready. Let's get into the facts. So let's start right at the foundation. MoR builds on something called recursive transformers. What does that actually mean, like in practice?
Yeah, a very clever concept. So instead of having a completely new set of parameters, weights, for every single layer in the network,
Uh-huh.
recursive transformers reuse a shared set of weights multiple times.
Okay, like recycling parts?
Kind of. Think of it maybe like a master chef. They perfect a few core techniques, right? A perfect sauté, a brilliant sauce.
Okay.
And then they apply those same honed techniques repeatedly and effectively to different parts of a meal, instead of needing a completely unique technique for every single step.
Ah, I see. So you get really good at a few things and reuse them.
Exactly. And this design, especially when using a smart strategy like the middle cycle approach, which is just an optimized way to structure these shared layers, it significantly cuts down the number of unique trainable parameters.
Which is a huge win for memory, I imagine, and efficiency overall.
A very big win.
Okay, so that parameter efficiency, the chef streamlining their prep, that's one piece, a massive piece. But you said MoR adds more.
It does. It doesn't stop there.
This is where it gets really interesting, I think. How did they make this unified approach work so smoothly?
Precisely. MoR isn't just weight sharing. It's a unified framework tackling efficiency from three angles at once.
Three angles, okay.
First, like we said, it ties weights to cut parameters, reusing that shared stack of layers across these recursion steps.
Right, fewer unique parameters, amortizing the memory cost.
Exactly. And from a distributed training perspective, when you're training on many machines, this works really well with techniques like FSDP, fully sharded data parallel.
FSDP, okay, that's the method for splitting huge models across GPUs, right?
Right, and it's efficient here because the same parameters, once gathered on a machine, get reused across all the recursive steps happening there. Saves a lot of communication.
Clever. Okay, what's the second angle?
Second, it routes tokens to cut redundant FLOPs. FLOPs being floating point operations, basically compute cost.
It routes tokens,
Yeah.
like individual words or parts of words.
Yes. It uses these lightweight routers, small neural networks, to dynamically decide how many recursion steps or how much processing each individual token needs.
So not every token gets the same amount of work done on it.
Exactly. This means MoR can focus the really demanding computation, like the attention mechanism.
The part that figures out how words relate, which usually scales quadratically, gets really expensive fast.
That's the one. It focuses that attention compute only among the tokens that are still active at a given recursion depth. It directs compute much more precisely.
Wow, okay. That sounds smart. And the third angle?
Third, it caches key-value pairs recursion-wise to cut memory traffic.
Ah, the KV cache. That's always a big memory hog in transformers.
A huge one. especially during generation. MoR selectively stores and retrieves these key value or KV pairs based on the recursion depth assigned to each token.
So it's smarter about what it keeps in memory and when.
Yes, and it improves memory access efficiency dramatically
Hmm.
without needing complicated fixes after the model is trained. It's built into the design.
Okay, so we've got the three pillars: tied weights, smart token routing, and efficient KV caching. But that routing part, the adaptive thinking, feels like the real game changer. How does it actually decide? How does that router work?
Yeah, that's crucial. MoR explores two main strategies for this dynamic routing. Each has its pros and cons.
Okay.
The first is expert choice routing.
Expert choice.
Yeah, imagine each recursion depth, like recursion step 1, step 2, step 3.
Right.
Imagine each one is an expert.
Okay.
That expert gets to choose its preferred top K tokens, say the top 10% or 20% of tokens it thinks need more processing to continue to the next step.
So the expert picks the token.
Right. The big advantage here is it guarantees a static compute budget. You know exactly how many tokens go to the next step, and it gives you perfect load balancing across your hardware by design.
Makes sense. But what's the catch?
The potential catch is something called causality violation during training. The router might sort of implicitly peek ahead at information from future tokens when making its choice, which you really want to avoid in language models that process things sequentially.
Ah, right. Can't
Right.
let it cheat by looking at the future. How does MoR handle that?
It addresses this by training what's called an auxiliary loss on the router itself. Basically, it gives the router an extra little training goal.
Like homework.
Sort of. To make sure it learns to predict reliably which token should be selected, even without seeing that future information during actual inference when it's generating text.
That's a pretty neat trick to get around the causality problem. Okay, so that's expert choice. What's the other option?
The second strategy is token choice routing.
Token choice. So the token chooses the expert.
Exactly. Here, each token is assigned a fixed recursion depth right at the beginning. One single routing decision up front.
Okay, so that sounds like it avoids the causality problem automatically.
It does, inherently, because the decision is made before any deep processing happens.
But there's always a but. What's the challenge here?
The challenge is load balancing. Since each token picks its depth independently, you might end up with, say, recursion depth 3 getting way more tokens than depth 2.
Ah, so uneven workload across the experts.
Right. So this often requires adding a different kind of extra objective during training, a balancing loss, to encourage tokens to spread out more evenly, or using specific loss-free algorithms designed to handle this. It can be tricky, especially if the experts or depths aren't all doing the same amount of work.
So two pretty different ways to manage the traffic. When you actually test them, what's the performance trade-off look like? Does one usually win out?
Yeah, the ablation studies, where they carefully test variations of the model, they consistently show that expert choice routing usually performs best.
The first one you mentioned?
Yes, particularly when they use that auxiliary loss we talked about and a pretty simple router architecture, like just a linear layer.
Why does it work better?
It seems to achieve a really clear separation in the router's decisions. The scores for tokens it selects are clustered very close to 1.0, and the scores for the ones it drops are very close to 0.0. It makes sharp choices.
I see. And token choice.
Token choice, while it nicely avoids the causality issue, tends to struggle a bit more with that load balancing, even with the balancing loss. Performance isn't quite as good usually.
Okay, that makes sense. So expert choice seems generally preferred for routing compute. Now, let's swing back to memory. The key value cache is such a big bottleneck. How does MoR optimize that specifically? You mentioned two strategies.
Yes, two KB caching strategies designed just for these recursive models. The first is recursion-wise.
KV caching.
Recursion-wise.
Yeah.
This one's very selective. Only the tokens that are actually routed to a specific recursion step store their key value entries at that level.
So if a token stops after step 1, its KV pairs don't get stored for step 2 or 3.
Exactly. And then the attention calculation at each step is restricted only to those tokens that are locally cached at that level.
Ah, so it keeps the attention computation more localized.
Precisely. It promotes what's called block local computation. Less data movement, less memory needed for the KV cache overall, less I/O traffic, and fewer FLOPs needed for attention at each layer. It's quite efficient.
Sounds very efficient. What's the second caching approach? Is it even more aggressive?
It is, yes. It's called recursive KV sharing. This one is even more aggressive on memory saving.
Recursive sharing. How does that work?
It cleverly uses the fact that all tokens have to go through at least the first recursion block, the first set of shared layers.
Right. Everyone starts at the beginning,
So it caches the KV pairs only at this initial step,
only at step 1.
exclusively. And then it reuses those same KV pairs across all the subsequent recursion steps.
Wow. So step 2, step 3, they all look back at the KV cache from step 1.
That's the idea. It ensures all tokens can still access the past context without needing to recompute or store KV pairs at deeper levels.
That must save a ton of memory and compute, especially during the prefill stage when the model processes the initial prompt.
It does. It can significantly cut prefill latency and the memory footprint by skipping the KV projection and storage at those shared depths.
Okay, that's fascinating. Again, we have this trade-off dance between performance and memory savings. Recursion-wise sounds super efficient, but maybe restrictive. Recursive sharing sounds memory frugal, but maybe less precise. Which one tends to be better in practice for more?
Well, the recursion-wise caching, the super selective one, while highly efficient, did show a slight dip in performance compared to the recursive sharing method in some tests.
Why might that be?
It suggests that maybe only attending to the tokens active at that specific step might be perhaps a bit too restrictive sometimes, maybe losing some useful context.
Okay.
But what's really interesting is that recursive KV sharing, the one that caches only at step 1, turns out to be surprisingly robust. Even in these models where parameters are already shared across layers,
Robust how?
it holds up well. And even more, it can actually benefit the token choice routing strategy.
Benefit token choice.
Well, remember, token choice routing can sometimes be less precise in its decisions.
Right, the load balancing issue.
By providing all tokens access to that shared KV cache from step 1, it gives them extra contextual information that can actually help compensate for slightly less accurate routing decisions.
Ah, so the shared cache helps make up for imperfect routing. That's a neat interaction.
It is. It offers a different kind of trade-off, one that can be really favorable for overall system performance and memory usage, especially with token choice routing.
Okay, this is all technically very cool, but for people actually using or building these models, the big question is, does it work? Does MoR actually deliver on this promise of, big model quality without the huge cost? What do the results show?
They absolutely do deliver. The empirical validation, the actual test results, are really compelling. They tested MoR across models ranging from about 135 million parameters up to 1.7 billion.
So a decent range of sizes.
Yes. And the results consistently show MoR forming what they call a new Pareto frontier. Better efficiency for a given level of performance.
Okay, give me an example, like same training budget.
Right. So under an equal training compute budget,
Yeah.
let's say 16.5 quintillion FLOPs, a massive number,
Whoa.
and MoR model, using that preferred expert choice routing and 2 recursion steps, it achieved lower validation perplexity. That's a measure of how well the model predicts text. Lower is better. And it surpassed the standard baseline transformer in average few-shot accuracy.
Better performance?
Yeah, 43.1% accuracy versus 42.3% for the baseline. But here's the kicker. It did this using nearly 50% fewer unique parameters.
Half the parameters, but better performance with the same compute budget. How?
Because MoR's computational efficiency is higher. It could process more training tokens within that same FLOP budget. It learned more from the data using the same amount of raw compute.
That's a huge advantage. What if you flip it? What if you fix the amount of data seen and look at compute savings?
They did that too, to really isolate the architectural benefits. So fix the number of training tokens at, say, 20 billion. The MoR model, again with 2 recursions, it outperformed both the standard vanilla transformer and a baseline recursive model that just shared weights but didn't have the smart routing or caching.
Better performance again.
Lower validation loss, higher accuracy. And it did this using 25% fewer training FLOPs.
25% less compute for better results on the same data.
Exactly. And that theoretical efficiency wasn't just theoretical, it translated directly into practical gains. 19% faster training time and a 25% cut in the peak memory needed during training.
Those are real-world numbers that matter. Reduced time, reduced hardware costs.
Absolutely. Tangible benefits for any lab or company.
And does this advantage hold up as you scale the models bigger? Or does MoR maybe lose its edge at larger sizes?
It seems to hold up remarkably well. MoR consistently did better than the recursive baselines across all the sizes they tested, from 135 million up to 1.7 billion parameters, and across different compute budgets, too.
Okay.
Now, the very smallest scale, 135M, it might slightly underperform a standard transformer initially, but that gap closes really fast.
And then?
At scales above about 360 million parameters, MoR starts matching or even beating the standard transformer in performance. even though it has roughly only one-third the unique parameters because of the layer tying.
One-third the parameters, matching or beating performance. That's impressive scaling.
It is. And its scaling behavior, how its performance improves with more compute, seems to favor making the model bigger rather than just training longer on more data. This suggests it might be less data hungry than standard models, another efficiency point.
Less data hungry. That's interesting too. Okay, training is one thing. What about inference? Actually using the model to generate text day to day. Does MoR speed things up there? Because that's where ongoing costs really live.
It definitely does. MoR provides a significant boost to inference throughput too, partly through its early exiting mechanism tokens finishing early free up resources, and partly by enabling a technique called continuous depth-wise batching.
Continuous depth-wise batching.
That's complex.
Yeah.
It's a bit like continuous batching for standard models, but adapted for MoR's different depths. The key idea is to immediately replace sequences that finish generating text with new incoming requests, specifically filling slots at the recursion depth they need.
So it keeps the GPU constantly busy across all of the different processing depths.
Exactly. High, consistent GPU utilization. And the result, for instance, one MoR model configuration, MoR 4, achieved up to a 2.06 times speed up in inference compared to a standard baseline transformer.
Double the speed.
Up to double, yeah. Even when that baseline model was also using a form of continuous batching.
Wow. That directly translates to faster responses for users and lower costs for running the service.
Absolutely. Lower operational expenses, faster applications. It's a big deal for deployment.
You know, when you first mentioned this adaptive thinking, it really made me think about how we read. Sometimes you skim, right? Other times you hit a complex sentence and you pause, you reread, you really dig in.
That's a really good analogy.
Is that kind of what MoR is doing? Is it deciding which tokens are harder and need more mental effort, more recursion steps? How does it know?
That's a great question, and it touches on one of the coolest parts of MoR, I think. The way it allocates recursion depth isn't random at all. It actually seems to reflect the semantic importance of each token.
Semantic importance, you mean its meaning or significance in the sentence?
Precisely. It's like the model is learning, implicitly, which words or concepts require more thought to process correctly.
So it's literally assigning more compute, more recursion steps to ones that are more meaningful or complex. And you give an example.
Yeah, qualitative analysis shows this quite clearly. They looked at which tokens went through more recursion steps.
And what did they find?
For instance, the very first token of a sequence, like people in one example, often went through the maximum number of steps. Makes sense. Got to set the context. And then content-rich tokens, words carrying significant meaning like intensively confident or drugs in their examples. Those also tended to pass through 3 recursion steps, the maximum in that setup.
Deeper processing for important words. What about less important ones?
Function words like and or punctuation like dank, they typically only traverse 2 steps. And words with sort of moderate semantic importance might only undergo a single recursion step.
Wow, so there's a clear pattern. It's learned to align the compute effort with how important or difficult a token seems to be.
Exactly. The routers aren't just random selectors. They're learning a meaningful allocation strategy, optimizing processing at a very granular token-by-token level.
So it's not just faster overall, it's genuinely smarter about how it uses its resources. That's fascinating. Okay, and what about this test time scaling concept? How does that fit in?
Right. MoR enables this really interesting capability, test time scaling.
What does it mean?
It means that going deeper in recursion using more steps doesn't just add more raw compute. Each subsequent step can actually specialize further. It refines the token's representation, its thought process, if you like, at that particular depth.
So deeper recursion equals better refinement.
Leading to better performance, yes. Directly during inference, when you're generating text. The cool part is you can potentially improve the quality of the output simply by allowing more recursion steps at test time.
Without retraining the model.
Without retraining the model at all.
Yep.
You could, in theory, dynamically adjust how much effort the model puts into a generation based on the task or the quality you need.
That's incredibly flexible. Adjust quality on the fly without expensive retraining, huge practical advantage.
Definitely.
Okay, wow. So let's try and wrap this up. We've taken a really deep dive today into Mixture-of-Recursions MoR, and it feels like a genuinely unified transformer architecture, really aiming to redefine efficiency for these large language models.
Yeah, it tackles multiple things at once. Parameter sharing through tide weights.
Right. Reusing those layers. Then the adaptive recursion depth, using those smart routers to send tokens for more or less processing.
Based on need. And finally, that really efficient key-value caching tailored for the recursive structure.
And the result is doing all this without really compromising the model's quality, its performance.
Exactly. By dynamically assigning that recursion depth via the routers and selectively caching states, MoR manages to significantly cut down both the compute and the memory demands.
Which brings us back to the start. It means we're getting closer to having large model capabilities, that high performance, but at a fraction of the cost.
Making powerful AI potentially more accessible, definitely more sustainable, and just more practical for a whole load of different applications.
It really feels like a significant step forward.
It does. And, it leaves you thinking. If more models can learn to adapt their thinking depth per token and align it so well with semantic importance, what's next?
What if future versions could go even further?
Right. What if they could learn to dynamically adjust their thought process, not just for tokens, but for the complexity of the reasoning chain needed for a particular query?
So allocating more thought, not just to words, but to entire lines of reasoning.
Maybe. Could that lead to AI systems that are not only more efficient, but maybe even more interpretable? We could potentially see how it decides to allocate more reasoning steps.
More efficient and more understandable AI, what might that unlock? For tasks beyond just generating language, maybe? True adaptive intelligence.
It's definitely a provocative thought to consider for the future of AI architecture. Where could truly adaptive, insightful AI take us?